Okay, now we're going to shift to section 5.4 in the book. This is a good section, and I really encourage you to read this section. It has to do with ideal and practical filters. So real quickly, remember that an ideal filter has no distortion. That means constant gain wherever we have a signal that we want, and linear phase, right? So gain means it doesn't depend. Constant gain means it doesn't depend on frequency. Linear phase means when we look at the phase, it's a straight line through the origin. Okay, and that's the linear phase requirement. It guarantees that every frequency in our desired signal has the same delay. Okay, all right. So now we're going to talk about frequency selective filters. We've kind of been talking about frequency selective filters, but now we're going to get serious. Okay, they're non-distorting, so they're ideal, non-distorting, but they're designed to remove specific frequency bands. We'll start with a band pass filter. This is designed to pass certain frequencies. Very common, like in radio, you want to pass the channel that you're listening to and block all the adjacent channels. It's called a band pass filter. In this case, we're gonna pass frequencies between some omega L and some omega U. Everything in between, we're going to block. The absolute value sign is just here so that it describes both the negative and positive frequencies. So when we graph this thing out, we see that we've got constant gain whenever the frequency, the magnitude of the frequency is between omega L and omega U. And we're assuming G is equal to 1 here, okay? So without loss of generality, we're going to say an ideal bandpass filter has this response. Phase response, linear. We want it to be non-distorting both in amplitude and in phase. I draw dotted lines here because in these regions where the frequency response is 0, no signal, no noise, no nothing gets through. So if nothing gets through, we don't really care if nothing gets if noise gets phase distortion or not. Okay, so this is the frequency response for an ideal band pass filter. A real simple example. Suppose the lower and upper frequencies are pi over 10 and 3 pi over 10. So that describes the edges of this pass band. Suppose the input looks like this. This is the input signal. It's got a 1 plus cos 2 pi over 10 n. Find the output. Okay, here's the input, find the output. Well, this term is a DC term. DC. It has a frequency is 0, right? So it's going to show up right in here. Here's where that DC term, it's going to get completely blocked. It's going to get a gain of 0 going through the filter. So it comes out the other end 0. On the other hand, 2 pi over 10 falls within the passband from pi over 10 to 3 pi over 10. It's right there. So it's going to get passed with amplitude preserved. The gain of the filter is 1, right? So it's went in with a gain of 1. It's coming out with a gain of 1. And it's also going to get a delay of ND. So ND defines that slope. Okay, so this filter will block low frequencies past that anything in that range. All right, just some quick remarks about this. First is that these we're only drawing the frequency response from 0 out to from minus pi out to pi. And within that range, we see these, like here's a bandpass filter. You have to keep in mind that this is just part of the picture. We're only showing the principal range. And if we were to draw this out, we would see that this whole picture repeats every 2 pi. Right? So there's 2 pi. And we get another replica of this out here at 4 pi, etc. Okay, so we're only really interested in what happens in the principal range. Everything where the filter response is 1 is called the passband. Everything in that range is a passband. And everything where the filter has 0 response is called the stopband, because we pass stuff in the passband, stop stuff that we don't like in the stopband. Again, we already said this before, but the phase response, we don't care if it's linear phase in the stopband. We can't really distort noise any more than it's already distorted. And finally, the bandwidth. Bandwidth is defined, as we've discussed before, it's only positive frequencies. So it's omega L minus omega U. All right. Well, quickly we can review some of the other filter types. There's an ideal low-pass filter. That means unit gain for frequencies below omega C, and that of course includes minus omega C, so the minus frequencies. Anything in this range gets passed. Anything above that frequency gets blocked. Here we're starting to condense our drawing, and I think you guys don't mind. We're just showing the magnitude and the phase drawn on the same graph. And here we're showing linear phase, so it's non-distorting in phase, and it's constant gain in the passband, and so it's non-amplitude distorting. WC, omega C, is called the cutoff frequency. Here's an ideal high-pass filter. So a high-pass filter is going to block the low frequencies and pass all the frequencies above some specified cutoff frequency. So this is called a high-pass filter. Here's a good test question. Who knows? I can rewrite this test question in various ways. What does a high-pass filter look like if you have to graph it from pi, that should be a minus pi, out to 5 pi? And just like I did in the example above, you see that the high-pass response is just replicated every 2 pi. So we take this thing and we see that it looks just the same if I go, so this thing that I've outlined is just a reproduction of this. And here's another reproduction centered about 4 pi. And there's another reproduction centered about 6 pi. So know how to do that.